So, energy level 2. In energy level 1, there's only one orbital, the 1s orbital. In energy level 2, there's two sublevels now. We have 2s and 2p sublevels. The 2s, again, has one orbital. S sublevels always have one orbital. P sublevels have three orbitals, as we see the drawings here. The p on the x-axis, p on the y-axis, p on the z-axis. All three orbitals have the same shape and same energy. They are just in different orientations in space. And that is one orbital. It can contain up to 2 electrons as long as the electrons have opposite spin. The p orbitals have the first node. And this shows some of the wave-like properties of electrons, like noise-canceling headphones. When two waves are in phase, they combine constructively, and you get a much bigger wave. But when two waves are completely out of phase, they destroy each other. Like a noise-canceling headphone will make sound exactly opposite of what it thought you were going to hear. Oops, let's draw that better. So if the wave is exactly opposite, it'll cancel out and you will have no sound. Or in this case, the wave destroys itself and you cannot find the electron at the node. So you can find the electron in here or in here, but you will never find the electron at the node because the wave properties are in the destroyed state. So you can have 6 total electrons in a p sublevel because there are 3 orbitals in a p sublevel, and each orbital can contain up to 2 electrons as long as the electrons have opposite spin. Principal energy level 3. Now we have 3s, 3p, and 3d orbitals. Remember, in the first energy level, there was only the s sublevel. In the second energy level, there was an s and p sublevel. Now in the third energy level, we have s, p, and d sublevels. And a d sublevel has 5 orbitals, so up to 10 electrons. And if you take an inorganic chemistry class, which is third-year chemistry in college, then you'll double down on the transition metals and the d orbitals, because the transition metals, that is, their chemistry is that of the d orbitals. The 5 d orbitals don't have the same energy. Again, if you take more inorganic chemistry, you'll get into what they call crystal field splitting. And so depending on the orientation of the ligands binding a central metal atom, that can change which of these orbitals have what energy compared to each other. But that is for a more advanced class. We're not going to worry about that right now. As there can be 5 d orbitals, each orbital can have a maximum of 2 electrons. You can have 10 total electrons in a d sublevel. So here we see 1s, then 2s, then 2p, then 3s, 3p, then 3d, 4s, 4p, 4d, and then 4f. The f's don't come up much in this class. That is the chemistry of the inner transition elements. If you look at your periodic table, you'll notice 2 rows at the bottom, and f sublevels have 7 orbitals. Notice you'll have 1, 2, 3, 4, 5, 6, 7. There are 7 orbitals in an f sublevel, and each orbital can have 2 electrons. You'll notice that your actinides and your lanthanides are 14 across. So your inner transition metals are the f block, and that starts at energy level 4. So there is no such thing as a 1p, a 1d, or a 1f. There is no such thing as a 2d or a 2f, and there is no such thing as a 3f. After energy level 4, 5 and on have all of these sublevels and more. And again, the PowerPoints don't even go into the shape or drawings of the f orbitals. That would come up in the third-year chemistry class. So what is the maximum number of electrons in a 4d sublevel? Well, a d sublevel can have 5 orbitals, and each orbital can have 2 electrons. That's 10 total. What is the maximum number of electrons that can occupy the n equals 3 energy level? Well, we have a 3s, a 3p, and a 3d level. And the 3s has 1 orbital times 2 electrons, that's 2. The 3p has 3 orbitals times 2, that's 6 more, I have 8 electrons. And the 3d has 5 orbitals, that's times 2, that's 10 electrons. So 18 total electrons. 2 go into the 1s orbital, 6 can go into the 3p orbitals, 10 can go into the 5d orbitals, for 18 total electrons going into these 9 total orbitals. Hydrogen. Now we're going to start looking at the atomic structure of the first 18 elements. How do we build them up? Start at the lowest energy level and keep building up. Your lowest sublevel will always be S. Your second lowest sublevel will always be P. Your third lowest sublevel will always be D. And your fourth lowest sublevel will always be F. That'll be the highest energy one. So in this class we fill up S's, P's, D's, and F's. In more advanced classes, when you get more into the D's and F's, there's a lot of exceptions and nuances there. For this class, we're not going to worry about that. So, our nomenclature. The big number tells you what energy level the electrons are in. The letter tells you what sublevel, S, P, D, or F. And the superscript tells you how many electrons are in that sublevel of that energy level. And so, we use a box as a simple diagram for an orbital. And inside a box you can have up to 2 arrows, but they must have opposite spin. And in general, by convention, chemists always put up spin first and then down spin. Although technically it's not wrong if you do it the other way around. So it's just typical to put up spin, then down spin. So hydrogen has 1 electron. So we put it in the 1s orbital. Then helium has a second electron. This fills up the 1s. And as that's the only orbital in the n equals 1 energy level, we have a full energy level. And you're going to notice that whenever you have a full energy level, you have a noble gas, because having a full energy level is super stable. So this is actually a full energy level, because in the first energy level, there is only a 1s orbital that can only contain up to 2 electrons. So then when we get a third electron, now we're in the second energy level. 2s1. Beryllium, 2s2. Now when we go to boron, we start filling up the 2p's. In general, things in nature like to spread out. And so with the p orbitals, because they're all equal energy, each one gets an electron, and only when they're forced to do they double up. It's like people taking a Greyhound bus ride. When you first get on the bus, you claim 2 seats to yourself because you like to spread out. It's only once everyone has claimed 2 seats and there's no more empty seats, and people keep coming onto the bus, only then do you start doubling up because you have no choice. And the electrons are the same way. If they have the option, they like to spread out and have some personal space. But when they're forced to, then they'll double up. And again, once they get to neon, we have a completely full n equals 2 shell. Whoops. A completely full n equals 2 shell. 1s2, 2s2, 2p6, which gives us neon. So here we see our first 10 elements. Notice, when the first energy level is full, we have a noble gas. When the second energy level is full, we have a noble gas. If we keep going, once the third energy level is full, we have a noble gas. So after 2p6, we go to the next row on the periodic table. 3s1 for sodium, then 3s2 for magnesium, then 3p1 for aluminum. Then you notice, just like before, each orbital gets 1 electron. They all have parallel spins. And then they double up when they're forced to until we have argon. A completely full n equals 3 shell gives us a noble gas. Valence electrons have a special place in chemistry because all chemistry is done with valence electrons. The inner electrons are held too tightly to do any chemistry. The nucleus is holding them so tightly they have no freedom and they can't do anything. So only the outermost energy level, only the valence electrons have the ability to enter into chemical reactions. How do you know what electrons are valence electrons? They're all the electrons in the outer energy shell. And that includes all the sublevels. So here for oxygen, oxygen has 6 valence electrons because I have 2 energy levels, 1 and 2. 2 is the biggest one. All the electrons in the n equals 2 principal energy level are valence. So I have 2 valence electrons in the 2s sublevel, 4 valence electrons in the 2p sublevel. But all sublevels count, and that's some place where students get confused because some of the sublevels are higher energy than the others. But for valence electrons, every single electron in the highest principal energy level is a valence electron. So how many valence electrons does phosphorus contain? If we find it on our trusty periodic table, we'll notice it's in row 3. Its valence shell is n equals 3, and that's 3s2, 3p3, 5 valence electrons. So we have 3 energy shells, the n equals 1 shell, the n equals 2 shell, and the n equals 3 shell. Of those 3 numbers, 3 is the biggest. Therefore, the third energy level is the valence shell. And there are 5 electrons in the third energy level. 5 valence electrons. Which element would have this following configuration? That'll be argon. 1s2, 2s2, 2p6 takes us to neon. 3s2 will take us to magnesium. 3p6 takes us to argon. And the way to double check that is just add up the subscripts, or superscripts. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. 18 electrons in a neutral atom, that's atomic number 18, has to be argon.